myself with the introduction to the 815 video. I thought I was, I guess, introducing 816. I forgot there's another lesson. Anyway, long story short, this is where all the multiple representations come together. So by the end of this, we should feel comfortable going back and forth depending on what they give us. Again, though, I always stop in a table first, just for convenience sake. So 877, writing a situation. Each representation below represents a different set of data. For each part, brainstorm a situation that could fit the data, provide enough information in your problem description so that someone else could generate the graph, table, whatever, be creative. So it looks like, I don't know, after 1 year, like, a population of a town was dwindling. At the beginning, there were 16,000 people in the town. At 1 year, there was only 14,000 people, and it continued on that rate forever. I guess you could say something like that. For B, started with $180 and you gain 22% compounded yearly, which would be an awesome. That would grow so quickly you wouldn't believe it. Anyway, here we can say 226 people lived in the country in 1980 and it gained 2% a population growth each year. So those would be some situations that would represent the graph, the equation, and the table. So here's the situation we want to turn into a graph. A virus has invaded Letitia's favorite mountain fishing lake. I'm sorry, I'm going to clear up some room here. Okay, so Fish and Game Department has determined that the rate of fish deaths will be 1/3 of the population each week if left untreated. So sketch a graph showing how many fish were left in the lake. So, I don't know. We could make a table first, or we can make the equation. I'm just going to make the equation. I think that should be enough. So, and then I'll make the graph from there. So we had 1,800 trout, and it says fish deaths will be 1/3 of the population. Well, if we're losing 1/3, that means we're keeping 2/3 of the fish. I hope that makes sense. So I guess thinking positively, right? We're keeping 2/3 of the fish because we're losing 1/3 of them. So what would that look like? Well, I guess, I don't know, if we said we were going by 500, say. This is a ugly, ugly graph, but we start with 1,800 fish. We keep 2/3 of them, so we end up with 1,200 on the first one. And then from there, we divide that by 3, so we get 400. So the second one, we're at about 800. And then from there, 800 divided by 3, so 600, a little bit less than 600. And so on and so forth. So you can see we're just going to keep multiplying by 2/3, and we're going to get the asymptote. Now it says, theoretically, will the trout ever disappear? Theoretically, they won't. Right? We do have the asymptote, but just think about it. It's just like the penny lab, where eventually it's going to get to 0. So sadly, it's hard to have 2/3 of a fish. When you get to 2/3 of a fish, usually you have 0 living fish. So I hate to go negative there. All right, let's go 816, part B, and keep going here. So we already answered 878. So we'll jump down to 879. Now we're going to go from a graph to an equation. So suppose the annual fees for attending a public university were $7,000 in 2010, which they're going to count 2010 as year 0, right? So this is 2010, but they're counting it as year 0. The annual cost can be seen in the graph. So it looks like it's going up 10% a year. So write the equation to model this. Well, we're starting at 7,000, and it looks like it's going up 10% a year, so I'll say 1.1, right? Use this model to predict the cost of living in 4 years. Well, in 4 years, I'm just going to say it's 1.1 to the 4th power, and then I need to multiply that by $7,000. So I'm going to get $10,248. So it's growing pretty quickly. If you're saving for college, you probably already know that. So what was the cost in 2000, assuming the rate of increase was the same during the time period from 2000 to 2010? Well, now year 2000 is going to be -10, right? That's going to be if 2010 is year 0, well, 2009 is -1, 2008 is -2, etc. So, right, so we're going to plug in -10. So I'm going to say that I'm going to go with 1.1 to the -10th power. Again, these calculators, that's a negative, that's minus. For some reason, they see those as different. So -10, apparently that didn't register. And then I'm going to multiply that by, it's really not, there we go. I'm going to multiply that by 7,000. And we get $2,698. So that's kind of a bummer. I'm weird. I did my dollar sign backward. I guess I was already making my 2. So year 2000, you're paying $2,600. Year 2020, you're paying. I'm sorry. Year 2014, you're paying. What the hell did I just do right here? Why did I do a 4? I don't know why I did a 4. I don't know. I guess I did year 2014, and I shouldn't have. So this is year 2014. I'm just sort of reading this question and realizing I made a mistake. So I don't know if whatever year you are, I don't know. Let's pretend you're going to graduate in 2022. You would have used a 12 there. So let's say 2022. You would have used a 12. Multiply that by 7,000. Now you're looking at $22,000 a year. So you can see that just keeps going up and up and up. So using the model, that what is the calculated cost for 2012? Are you confident about this value? Well, I mean, according to this, we're just going to plug a 2 in, right? We're going to go 2011 is a 1 and 2012 is a 2. So we'll just say I'm going to go 1.1 to the 2nd power, and I'll multiply that by 7,000. It's not registering that multiply. There we go. Times 7,000. And we get $8,470. And the question is, how confident am I? Well, I mean, I guess when this book came out, apparently in 2010, I wasn't very confident. But now I could easily go back and see how accurate that prediction was. But I don't choose to. So, but the point is, when you're making a prediction, you only have so much confidence, which isn't super high. Now, in 2012, the annual cost was actually $82.44. Why is it different? Well, apparently, cost of college didn't raise as much as we had predicted. All right, continuing along, equation graph. For each equation below, make a reasonable sketch. So here, I will say I will go by tens. It starts at 5, and then it starts tripling, so 15 to 45. So 0, 1, 2. That one grows pretty quickly. Here, we have 10, and then 5, and then 2.5, and then 1. So this would be 5, and this would be 10, and 0, 1, 2, 3. So it's going to dwindle rather quickly. Here, kind of a pain. Thanks, book. But if I'm making a just kind of an ugly sketch here, I guess we'll say this is 1, 2, 3, 4. And it starts at 1/10, and then it goes to 1/2, and then it goes to 2.5, and then I think it would go to like 7.5 is what I'm guessing, right? Because basically I'm just multiplying by 5. So 0.1 times 5 is 0.5. 0.5 times 5 is 2.5. 2.5, oh wait, no, that would be like 12 something. So yeah, that one would be off the charts there. So I guess we could put like a little break, and say somewhere between 12 and 13, we would have that 12.5. So not the world's greatest graphs, but whatever, good enough. And now let's go ahead and dump this, and we'll do 881 on a fresh sheet here. So as we go across here, situation. Use each of the situation below to complete the missing pieces of the web, or to practice moving from one situation directly to a specific representation. So here, 100 gram sample of radioactive isotope with a decay of 0.94. So I would say y equals 100 times 0.94 to the x. And again, I hope that makes sense. And that would be a decrease. You could definitely make better graphs than that for sure. The Math Club is fast becoming one of the most popular clubs on campus because of the fabulous activities it sponsors annually for Pi Day on March 14th. Each year, the club enrollment increased by 30%. If the club had 45 members this year, how many members should expect to have 5 years from now? So I guess we could say y equals 45. So I'll put 450. So y equals 45 times 1.3. And we'll put a 5 there, right? That's going to help us figure that out. Or we could have made a table. And we could have said 0 is 45. And then we could have just started multiplying by 1.3 until we got to year 5. That would have worked as well. On C, Barbara made a bad investment. Rather than earning interest, her money is decreasing 11% a week. Not good, Barbara. After just 1 week, she is down to $142.40. So think about that. After 1 week, she's at $142.40. And her multiplier is 0.89, right? She's losing. So if she divides 142.4, right? If she divides by 0.89, so 142.4 divided by 0.89, she'll go back to her starting amount, which is $160. So you can write that equation if you want. It looks like she started with 160. She has a multiplier of 0.89 to the x weekly. We're gonna just sort of go by week instead of by year there, so I don't want to divide by 52 and multiply by 52. If you were wondering that. I mean, we could have done that yearly, but it would have been way ugly. Larry loves music. He bought $285 worth of music using his credit card, and now he cannot afford to pay off his debt. If the credit card company charges him 18% annual interest compounded monthly, how does Larry's debt grow as time passes? Well, we would say 285. 285. 1 plus 0.18 divided by 12, right? Because it's 8. He's paying monthly. And we'll say there's 12 payments a year. So this would be the equation that we would use, which would actually equal y equals 285, 1.015 to the 12x. So that's how it would grow. I hope that makes sense sort of going around. Obviously, on the last ones, I didn't do all of them. I think that's something you could probably be able to do. But as always, feel free to reach out and ask questions if you have them.